All right, Assalamualaikum and good afternoon. Okay, we'll be continuing with the final topic in chapter 6, kinetic theory for an ideal gas. All right, so let's start with, what is kinetic theory? Kinetic theory is just the theory of how a gas moves in a certain situation. Okay, so here we have 4 assumptions. Okay, 1, there is a large number of molecules with mass and moving at random directions with a variety of speeds. Okay, the molecules on average are far apart from each other, and then the molecules only interact with one another when they collide, and the collisions of molecule with another molecule or the wall are perfectly elastic. All right, so why do we need to have assumptions? Okay, because 1, we cannot see gases doing all this. We don't know exactly how many number of molecules are there. Okay, but we know that each gas has their own mass. And then we don't know for certain in what direction a gas is moving unless we measure it. And then again, if we don't measure it, there is a variety of speeds. Okay, and same with number 2, 3, and 4, we don't know for sure, but these are the assumptions we do need to make calculation easier. Right? Okay, next, let's see here. The pressure exerted on a wall of a container of gas due to the constant collision of molecules can be calculated. Okay, again, if you want to calculate, you can, but it takes a lot of information and you need to do it meticulously. Okay. Now, consider the molecules are inside a rectangular container whose ends have areas of A and length of L, as shown in the figure 18.1, the figure side. Okay, it is found that the force exerted on the area by the collision of one molecule is given as such. F is the difference in M multiplied by V divided by the difference in T. Right, and then we have mv squared over L. Okay, next. The force due to all the molecules colliding with that wall is only given here. F is equal to M divided by L multiplied by N and then multiplied by the average velocity squared. Okay, where N is the total number of molecules. Okay, here there is a bar, a line on top of V. Okay, so if you remember your statistics, a line above just means it's the average. Okay, average number, or in here, average number of V, the velocity. All right, and then the force due to all molecules colliding with the wall, in all 3 directions are equal to this equation. And then you can get the next 3 equations by just manipulating the previous equations. Okay, so let's see here, pressure. If previously we were talking about force, now let's talk about pressure. Okay, is equal to a third, 1 over 3 of N multiplied by M multiplied by V, the average of velocity squared, and then divided by the volume. And then we also know that pressure, okay, we know that pressure is equal to F divided by A, and then volume is equal to I multiplied by A. Okay, so P is equal to F over A, we get it from your calculation of pressure, okay, whereas volume, okay, is just for the example given previously was a cube, okay, a cube. So you have the area, cross-sectional area multiplied by the length of that particular cube. Okay, so you have IL multiplied by A. And then, okay, when you simplify your equation, you get PV is equal to 2 over 3N multiplied by half mv squared. Again, this is the average. And then we also know, okay, from the previous equation, sorry, the previous topic, okay, PV is equal to NK multiplied by T. We can further simplify so that K, or here K is your kinetic energy. Okay, again, because there's a line on top, that means it's just the average kinetic energy. Okay, and then because we are talking about translational kinetic energy, then this is the average translational kinetic energy is equal to half mv squared. Okay, again, the average velocity, or 3/2 k multiplied by temperature. Right, and here we see from the equation given previously, okay, we can calculate the average speed of molecules in a gas as a function of temperature, where its value is equal to root mean square of the speed. Okay, VRMS. Okay, let's go through this equation first before I explain what is RMS. Okay, so VRMS is equal to the square root of V squared, the average velocity squared, and it's also equal to the square root of 3 multiplied by K multiplied by T divided by M. Okay, so what is RMS? Okay, so what is RMS? RMS, as was stated here, okay, the root mean square, okay, RMS root mean square of the speed, because it's the V is here, okay. So why do we want to find the VRMS? Okay, all right, so if you remember from your statistics, okay, statistics classes, okay, when you want to find the average value of a measurement, okay, you want to find the average value of a measurement, you will do x plus 1, x1 plus x2 plus x3, so on, divided by the number of samples you have. Okay, so if it's 3, then divided by 3. So x1 plus x2 plus x3 divided by 3. Okay, here we want to find the same thing. VRMS is just the average value, but we cannot use this equation here because of a situation where there is a positive and negative value. Okay, just think of it. Okay, so let's say the amplitude here is 5 and here is -5. Okay, we just want to find the average value, x1 here and x2 here. Let's, for example, that is what you're trying to do. Okay, so x is equal to 5 plus -5 divided by 2. You will get it is equal to 0. 5 minus 5 divided by 2, 0. Okay? But what can be seen is that this number is not correct. Okay, the average value for this situation is not 0. It is a value above 0. Okay, the effective average number is not 0. So we have to find another way to counter this negative part. So that's how VRMS happened. Okay, so what is it that we're doing here? Okay, so VRMS, if you look at the name itself, okay, root, mean, square. You are going to do all those three. Okay, root, mean, and square, but here we are doing it in the opposite direction. So root is the first word, the second word is mean, the third word is square. We're going to do square first, followed by mean, followed by root. Okay, what does it mean? Okay, right. So again, so let's say we are trying to find the average of x. Okay, so what happens is that we will be adding all your x's. Okay, x1 plus x2 plus x3, okay, plus x3 and so on. Okay, We want to do that, but first what we must do is we must square all the numbers. Okay, so x1 squared, x2 squared, x3 squared. Okay, next, when you have that, then you find the mean. Okay, so x1 plus x2 plus x3. Okay, because there are three numbers, then we divide it by 3. And this one is the same as the normal average number. Okay, how you want to find an average number. And then finally, the last step is just to square, to square root your whole number. Okay, why do we do this? All right, so again, let's look back at your graph. Okay, so we have a positive, negative graph. So what happens when you square this graph? Okay, so what happens when you square this graph? Okay, what will happen is that when previously there was a positive and negative graph, now you will only have positive peaks of your graph. Okay, positive number squared, you get a higher peak. Negative number squared, you will have a positive peak. Okay, so instead of your graph going like that, now it becomes like the one on top of your graph. So now we see that all your numbers are positive, and then you can find your average. Okay, so you find your average by the same method. X1, let's say here. Okay, let's use the same example as just now. Okay, so previously it was like that. Okay, x1 here, x2 here. We squared both numbers. Okay, we squared both numbers, so it will just happen like that. Okay, x2 here. All right, and then you want to find the average. Okay, you want to find the average is x1 plus x2 divided by 2. Okay, but because previously you've squared the number, now you have to root the number back. Okay, because initially you squared the number, now you have to root the number, square root the number. Okay, so here is again, you just want to find your average value. Okay, average value. Right, next. Okay, the average translational kinetic energy of the molecules in an ideal gas is directly proportional to the temperature of the gas. Okay, very straightforward. As temperature increases, your kinetic energy also increases. Okay. And then the average speed of a molecule in a gas as a function of temperature. Okay, if you look at this equation, it's also the same. As temperature increases, the average speed also increases. Right, for this example, okay, air is primarily a mixture of nitrogen and oxygen. Assume that each behave as an ideal gas. Determine the RMS speed of the nitrogen molecule when temperature is 20 degrees Celsius. Okay, this is very straightforward. Okay, you have your gases, nitrogen, you have oxygen, and then it is also stated that it behaves as an ideal gas. The mixture is an ideal gas situation. Okay, so you can straight away use VRMS because we know that VRMS is used in an ideal gas situation. Okay, and then you just put in your numbers. Okay, 3 KT. Okay, K is a constant, T is given. But remember to change from Celsius to Kelvin. Okay, and then, okay, here, what mass do you need to use? You have to use the mass for nitrogen. Why? Because it is given in the question, determine the speed of the nitrogen molecules. Right? Okay. All right, and for this exercise, as was mentioned before, Please try this exercise, okay, by yourself, try with your friends, okay, and submit to your lecturers to discuss further. And with that, that's it for chapter 6. Okay, thank you very much.